Hi guys, I hope everybody enjoyed the beautiful weather during the weekend. I hope you did something fun. Well, if you didn't, I will give you an opportunity to do some fun stuff. We are going to learn about the limits. And well, there are two options. You are either going to be in Mr. Hendrickson's calculus class, and if that's the case, then he will be extremely proud of you if you know how to calculate limits. If you are going to college and you possibly will be taking calculus and you know this stuff, you are ahead of everybody else. So either way, it's a win and win. And if you don't go to college and you are not going to be with Mr. Hendrickson, then you will know this, and that's the most important thing ever. Anyway, having said that, what are the limits? We've talked about limits already. So we talked about the limits, we talked about functions, rational functions, and we tested what would happen for our end behavior. So I will give you an example, and my example is going to be a function f of x that is described as f of x plus 2 divided by x minus 1. What do I know about this rational function? I know that because it has the same highest exponent both in the denominator and numerator in the denominator, that means that it is going to have a horizontal asymptote. What does this mean? If I make a very quick graph of this function, the horizontal asymptote is at y is equal to, and I take the coefficient that goes with the highest exponent. So in this case, it's 4 over 1, which is equal to 4. So here we go. Let's say that this is 4. Well, I could go a little bit farther. I know that the vertical asymptote is at 1. You will not have to do any of those graphs. I just want to show you what is happening. I am not going to graph this function, but what I do know because of the definition of the horizontal asymptote is that limit as x goes to negative infinity, my f of x is going to approach 4. The same thing, limit as x goes to positive infinity, the function is going to approach 4. Well, I put the arrow, it should be equal sign because that is the notation for the limits. So this is very important. This is something that you've already done, but I want you to remember what is happening is as my x values are going to get larger and larger and larger, your y values are going to be getting closer and closer and closer to 4, but never will go through 4. And then when x goes to negative infinity, the y values are also going to be approaching 4. Okay, so this is our positive infinity, negative infinity cases that we've already talked about. All right, let's look at another example. What is happening if I want to find the limit at a point? So here's a second example, and I am going to make a graph, and my graph is going to look like this. I am going to say that this is 1, I am going to say that this is 2. There's going to be a line, but I am going to leave the open circle right there, and I am going to say that this is 1. So what I want to find is I want to find what is the limit of this function that I am also going to call f of x as x approach 1. So what does this mean? And especially you may question this because I put this open circle, which means that the function doesn't have a value right there. But what the limit means is that I actually do not care what the value is exactly at that point. What I do care about is so as x approaches 1, what is the y approaching? So I want you to think about this for a second. As x's are getting closer and closer and closer from the left hand side, so let's say if I take 0, I am at 1. If I take half, well, I'm assuming that this is a nice linear pattern, I am at half. If I am at 0.6, I am at something, 0.7, 0.8, 0.9, 0.91. As my x's are getting closer and closer to 1, my y values are going to get closer and closer to 2. this is going to happen when I go from the left hand side, and this is also going to happen when I go from the right hand side. So because of this is happening both from the left and the right hand side, I know that the limit is going to be equivalent to 2. So notice what I am doing. I am predicting what the y value is as we are approaching the point that is being chosen. Okay, now if the limits are the same when you are going from the left side and the right side, then that is a limit, that is the value of the limit for this particular point. You will see that when something else will happen, if they are not the same when you are going from the left or right hand side, then we'll have to figure something else out. Okay, let's take a look at another example just for fun of it. I'm going to make a very similar graph. So this is 1. I am going to leave this circle open. So my idea is that I want the same points, 1, 2, and this is 1. But now I'm going to say that there's some point right here that does belong to this graph. So there is actually a value at x is equal to 1 for this particular function that I just graphed. However, what is the limit as of my function f of x as x goes to 1? So again, I do not care what that exact value is. What I care is what is happening as x approaches 1 from the left hand side. So again, look at this. If I take some value here, it's getting closer to what? Getting closer to what? Getting closer to what? Getting closer to what? And then we would go from the other way, the other direction. So you would, or you should notice that is also going to be equal to 2. Now, very soon we are going to start using this notation as x goes to 1 from the left hand side. My f of x is equal to 2. Limit as x goes to 1 from the right hand side. My f of x is also equal to 2. We did say this for the first example as well. But because both of those conditions are met, we can say that limit of f of x as x approaches 1 is equivalent to 2. All right, let's make this a little bit different. What would have happened if I now graph a graph that looks like this? And again, I'm going to try to use the same points. 1, we'll say it's 2. This is 1. So notice I graphed the line. I did not exclude any points. So now limit as x goes to 1. What is my y approaching? So notice in this case, the point is included and it's still going to be equivalent to 2, right? So those are the limits at the points. And this is something you will get to practice. But now, will the limit always exist? Let's try one more example. Well, 2 more examples, and then we'll go from there. So what would happen if I graph something that looks like this? 1, 2. I am going to say that this is one part of my function, and then I'm going to say that this is the other part of my function. Well, we can introduce some numbers on the y-axis, 1, 2, 3, 4, 5. Why not? 1, 2, and then we can go from there. So the question would be, what is limit as x goes to 2 of my function f of x that I did not define with an equation, but I did define it with the graph. So let's see. What would happen as x goes to 2 from the left-hand side? So limit as x goes to 2 from the left-hand side. So notice this is from the left-hand side. So whenever I would choose 0, I am at 2. If I choose 1, I am at 2. If I choose 2, I am at 2. Any value. So this is going to be equivalent to 2. What is going to happen? Limit f of x. If x, we are getting to x x is going to 2, but from the right hand side. So if I take any value here, so let's say 4, I am at 5, 3, I am at 5, 2.5, I am at 5, and notice that this is going to be equivalent to 5. Because those two numbers don't match, this does not exist. It's not defined. Okay, the limit of this function f of x that I graphed is not defined right here, because in order for the limit to be defined, it would have to approach the same number from both directions. All right, so something for us to remember. All right, and then one more type of examples. What if I want to translate the following statement into words? And we are actually going to use something that we just recently learned. So I am going to write this limit as n goes to positive infinity. I am going to use the sum notation. I is equal to 1, and then we are going to go to n. And then I am going to say 1/2 to the power of I is equal to 1. So notice we are not going to calculate anything. What we are going to show is we are going to show what is the meaning of this. So notice we are talking about the limit of what? The limit of the sum and what is the sum of? So if I is equal to 1, we know that we have 1/2. Then again, it's a sum, so I will put plus sign. Now the I is changing, so now we are going to take the next I, so it's 2, so this is going to be 1/4. Next one is going to be, if this is 3, then this is 1/8. And then we do see that this pattern is going to continue forever because we are going up to the nth term. And we know that the limit of the sum as this is going to happen. So we can say as the number of terms approaches infinity, is 1, right? And we talked about the series like this where we are adding those fractions, and because the next number is going to get smaller and smaller, this is going to approach 1, but it's never going to be equivalent to 1. Now, what if we switch this example and we are going to go the other way? So what I want to do is I am going to give you a statement. So 1/3 plus 1/9 plus 1/27 plus, and I am going to say that this is going to be equivalent to 1/2. So notice those are different kind of fractions. The denominator is 3, and then this looks like 3 squared. This looks like 3 to the power of 3. So would you be able to write this using limit notation? Well, I will help you with this one. So limit as n is approaching the positive infinity, I am going to use my sum notation, and I am going to say that first I is equal to 1. I am raising this to the first power. I am going to go towards the infinity, so whatever the nth term is. And notice that I didn't notice the pattern. So it's 1/3 to the power of I, and then we do know from what was given that this is going to be equivalent to 1/2, and that's it. All right, so that's that. And we are going to do a little bit of practice for this. Please make sure you come check with me if you have any questions. This is just the beginning of the limits. Well, that is going to test your limits. and make sure you start this from the beginning. This is a beautiful start for your calculus journey. So again, make sure you start it right, and enjoy it. Spend a good quality time with this, and of course have a great day.